And anybody that needs to can go back out after class today. Hey, Guillermo, good to see you. Thanks for being here. Hey, Star, I see you too, hopping in. Welcome, welcome. All right, so let's take a jump over to our Google Classroom here. So we have made it to the end of week 3. We are almost to the halfway mark of our school term so far. Write down that Guillermo and Estrella are here. All right, all right. So today we are jumping in, talking about how it is that these electrons are organized around the atoms that they are a part of. So Tuesday we started talking about electrons along with the protons and the neutrons. We talked about how the protons and the neutrons are hanging out in the nucleus and the electrons are kind of orbiting around the outside. We talked about how to figure out how many electrons that we have. And the main thing that we talked about is that the electrons and, whoops, where's my little marker? Hey, there it is. The electrons and the protons have to be the same, right? That was kind of the first big thing that we talked about with our electron, or the biggest thing that we talked about when we were trying to figure out how many electrons are there in an atom. Well, it's based on how many protons there are. Electrons are negatively charged because remember, if you get hit with electricity, you're going to have a negative time. So electrons are negative, protons are positive, and if we end up with the same number of them in our atoms, then they balance each other out. They cancel out and we have a neutral atom that does not have a charge in it. So the other main thing that we talked about with electrons is that they do not get to hang out with the protons and the neutrons in our nucleus here, right? So here we have hydrogen. Hydrogen is a super simple atom made up of 1 electron and 1 proton. The proton is here in the nucleus, but the electron doesn't get to go here. The electron has to go outside, around the nucleus. So hydrogen has its 1 little electron kind of floating here around the outside of the atom, the outside portion. However, one thing that I did not talk about on Tuesday, because I knew that we were going to get into it today, is that electrons do not just float randomly around the atom that they are a part of. It's not like they're just kind of thrown out to the outside and then they're circling around all together. No, 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 no. Instead, they are set up in a particular way around the atom. They're organized into different levels, essentially. And we call those levels electron shells. So each atom, depending on how many electrons that it has around it, has these different shells. You can think about them kind of like the layers of an onion. All right, the onions have the outer layer and you peel it away and there's a smaller inner layer and then you peel that away and there's an even smaller inner one. The electron shells work kind of the same way. There's a layer that's closest to the nucleus, so we call that the first shell. And then the other shells kind of build on top of that. So the second electron shell is 1 more outside of that. And then the third electron shell is around the second electron shell. So we have the closest in first shell, and then on top of that is the second shell, and on top of that is the third shell. And the main thing that we're going to talk about today is that there are specific rules, specific laws about how many electrons you can fit on a shell. It's not just some go on here and then some more go on here and some more go on here. And they're not all distributed equally. Instead, there are laws around how many electrons go on each shell. So for our first electron shell, for example, it can fit a maximum of 2 electrons on it. So for our super duper tiny atoms, this is fine. We already talked about hydrogen right here. He's got one little electron out there. Helium, which you guys were working with for your daily assignment yesterday, helium's got 2 electrons on the outside of it. So helium has a totally full first electron shell. And that's all it needs, because it's just got these 2 here. But what about if we go up one from there? Like, say, to the next atom in our periodic table, which is called lithium, like the stuff that goes in batteries for things like cell phones and computers. Lithium has 3 electrons. That means that lithium can fit 2 electrons on the first shell, but now that shell is full. We can't fit any more electrons on there. So that last electron, that third one, has to go on our second shell right here. So lithium has 2 electrons on the first shell, but then it gets full. So our third electron goes on the second shell. 3 electrons total, 2 on the first and 1 on the second shell. The second shell and the third shell, which is the biggest one that we're going to be talking about in this class, can both fit a maximum of 8 electrons. So these numbers here represent the maximum number of electrons that can fit on that shell. The first shell fits a maximum of 2. Shell number 2 and shell number 3 can fit a maximum of 8 electrons. So lithium's fine because it fills up its first shell, can put 1 more on the second shell, and then it's done. It's run out of electrons. It's put them all on the correct shells. It's good to go. Carbon has a few more electrons than lithium. Carbon has 6 electrons. So carbon can fit 2 electrons on the first shell, but then the first shell is full, so we got to move to the second shell. So the remaining 4 electrons out of the 6 go on the second shell. So that's kind of the process by which you can figure out which electrons are supposed to go on which shells. You always start by filling up the first shell. When that gets full, you move on to the second shell. If that gets full, you move on to the third shell, and so on and so forth. There are higher electron shells. I think there's up to like 7 or 8 electron shells. We're not going to worry about all those in this class. We're just going to focus on the first 3. So neon here is a pretty cool little atom because neon has a full first shell and a full second shell. Neon has an atomic number of 10, which, if you remember from Tuesday, means that neon has 10 protons, which means that neon also has 10 electrons. So neon, the stuff that goes in like the signs in front of convenience stores and stuff like that, neon can fit 2 electrons on the first shell, but then that one's full, and then it can fit its remaining 8 electrons on the second shell. So 2 electrons plus 8 electrons gives us 10 electrons total, and that is how many electrons are in neon. So neon has a full first shell of 2 electrons and a full second shell of 8 electrons. So neon is a happy little atom. He's got all the electrons that he needs. What if we add on an electron? Say we go up in the periodic table and we go from neon to sodium. Sodium has a chemical symbol of Na. It's one of those weird atoms that has a symbol that doesn't exactly match up with its name. That happens sometimes. It's basically just because the name in English doesn't match up with like the original Latin name or something like that. So this happens sometimes. Gold is Au on the periodic table. Silver is Ag. It just has to do with what like the original ancient Greek or Latin names or whatever this substance was before they got English names. I don't know what sodium's was, but it was shortened to Na. So now sodium has the chemical symbol of Na. Sodium has one more electron than neon. Sodium has an atomic number of 11, which means that sodium has 11 protons and 11 electrons. So we can fit 2 on the first shell. We then have 9 more. So we can fit 8 on the second shell. So now we have a full first shell and a full second shell, but we've only put down 10 of our 11 electrons. So that last electron, that 11th electron, gets to go hang out on the third shell all by itself. So 2 on the first shell plus 8 on the second shell plus 1 on the third shell gives us 11 electrons for sodium. Silicon has a couple more. Silicon has 14 electrons. So again, start at the first shell. We can put down 1, 2, 12 electrons to go. First shell is full, so we got to move to the second shell. We can put down 8 electrons on the second shell, but now we've only put down 10 out of our 14 electrons that make up silicon.
Excuse me.
1, 2, 3, 4 electrons go on the third shell right here.
Excuse me.
Yes, go for it.
Am I the only one that's lost?
It is totally fine.
I feel lost and
It is totally fine if you are lost. We're going to be doing a whole bunch of these examples today to make sure that everybody gets it.
Yes, I need the extra help too.
No worries. We'll do a bunch of examples together to make sure that everybody is on the same page. All right, so the centers of these atoms, like where the names are, where the symbols are, that's our nucleus. So those are the protons and neutrons hanging out together. And then the electrons go on the outside, and they're organized in these shells. So like if we look at the biggest electron example that we're going to talk about today, it's the atom argon. So argon.
so is the first shell closest to the atom, or?
Yep. Mm-hmm.
Okay.
The first shell is like
So
the
it's that
closest
first
in
line.
to the atom. Yeah, the first shell represented by this first line here is the closest in to the atom. And then the second shell is a little bit further away. And then the third shell is a little bit further away than that.
Okay.
So exactly, those lines here represent the electron shells, and they represent kind of how close or how far away they are from the center of the atom, that nucleus, where the protons and neutrons are hanging out. So if we want to fill up all of our 3 shells, we can look at an atom like argon. Argon has an atomic number of 18, which means that argon has 18 protons and 18 electrons. So if we want to figure out where these electrons are going to go, we always start with the first shell. So we put the first 2 electrons of argon on its first shell here. That's 2 down, but we still have 16 more to go. So we have to move on to the second shell. We can put 8 electrons down on the second shell of argon because our second electron shell can fit a maximum of 8 electrons. So 2 electrons on the first shell plus 8 electrons on the second shell gives us a total of 10 electrons so far, but argon has 18 electrons. So that means we're going to have to put some electrons on the third shell. Specifically, we're going to need to put 8 more electrons down. Those final 8 electrons of argon go on the third shell. So argon has a completely full first, second, and third electron shell. 2 electrons on the first shell, 8 electrons on the second shell, and 8 electrons on the third shell, giving us a total of 18 electrons, which are how many are in argon atom number 18. So that is sort of the basic process of figuring out how to put electrons in their shells around an atom. You figure out how many electrons that atom has. You start by filling up the first shell. If you put down 2 electrons and you still have some left over, you move on to the second shell. If you put down 8 more electrons and still have some left over, you move on to the third shell. So we are going to do more examples of these, including some examples that we do together. So don't worry if you're not 100% getting it yet. But does anybody have any major questions so far? Anything that you're totally confused about with these electron shells?
All of it.
All of it? Okay, well, don't worry. We are going to go through some more examples in case you can't think of anything specific. Right.
Is it always going to be 2 on the second thing and then 8 on the last one?
So it's always going to be 2 on the first, 8 on the second, and 8 on the third.
Okay.
But yeah, so that's the absolute maximum number of electrons that can fit on these shells. There cannot be more than 2 electrons on the first shell. There cannot be more than 8 electrons on the second shell. And there cannot be more than 8 electrons on the third shell.
So the shells are the rows.
Yeah, the shells are these little lines.
So can there be like 6?
Sure, like carbon right here. He has 4 on his second shell.
But it's 6.
6 total, exactly.
Yeah. Oh.
So yeah, it doesn't have to be 8, but there can be up to 8 on the second shell. That's like the maximum number. But if you only have 6 electrons total, like carbon right here, you put 2 on the first shell, then move up and put the remaining 4 on the second shell.
So why is it important to know about electrons and protons and neutrons?
So these are what make up the atoms, and atoms make everything in the universe. You are made of atoms. Your family is made out of atoms. Your house, your car, it's all made out of atoms. And so how many of these particles are in an atom helps figure out how they can combine atoms together in different ways to create like new substances and new products that they're trying to make.
Okay, that makes sense because I didn't understand what atoms and stuff did.
Yeah, so atoms are, again, super incredibly tiny, small, microscopic particles, but they make up everything in the universe. So everything that you've ever interacted with in your life, everything on Earth, everything on Mars, everything in our sun, everything in the galaxy, in the universe, it is all made out of atoms. All right, great question so far. All right, let me show you a couple more examples of these electron shells, and then we'll work on some examples together. I'll have you guys help me build some electrons. So here we have some kind of expanded versions of these electron shells that, to me, help you guys see it a little bit better, a little more clearly. So nitrogen is a pretty common atom in our environment. The atmosphere that we breathe, we need the oxygen that's in it, but it's actually made up of about 70% nitrogen, just kind of floating out there. Nitrogen has an atomic number of 7, which means that nitrogen has 7 protons and 7 electrons. So here's our little nitrogen nucleus, and here are our electron shells. We can put 1, 2 atom electrons down on the first shell, but now the first shell is full and we still have 5 more electrons to go. So we move out to the second shell and put down 1, 2, 3, 4, 5 electrons. So 2 on the first shell plus 5 on the second shell give us a total of 7 electrons, which is exactly how many are in nitrogen. So we started with that first shell, we filled it up with 2, and then we moved and put the rest on the second shell. Neon, we've already talked about with that last example. It's that one that has a full first and second shell. So not all atoms have a full first, second, third, whatever shell, but neon is one of the few that does. So 10 electrons in neon, 2 go on the first shell. We then have 8 left over. So the remaining 1, 2, 3, 4, 5, 6, 7, 8 electrons go on the second shell of neon. So no more can fit, but luckily for me, neon, we don't need any more. We've hit our 10 total electrons. If we did have a atom that was a little bit bigger than neon, say something like aluminum, like the stuff they use for the foil in your house, aluminum is an atomic number 13, which means aluminum has 13 protons, and importantly for us today, 13 electrons. So we always start with that first shell. That has to get filled up first. So we put 1, 2 down on the first shell, but we still have, what's 13, 12, 11 electrons left over. So we can put 8 more down on the second shell, but now the second shell is full and we still have 11, 10, 9, 7, 6, 5, 4, 3 electrons left to go, right? We have 13 total. You put down 2, you put down 8, that gives us 10, but we still have 3 more electrons to go. So we've got to move out to the third shell and put 1, 2, 3 electrons down on the third shell of aluminum here. So aluminum's got 13 electrons in total, 2 on the first shell, which is full, plus 8 on the second shell, which is also full, plus 3 more out on the third shell, gives us 13 electrons in aluminum. So we figured out how many electrons are in our atom. We started putting those electrons on the first shell. When that got full, we moved out to the second shell. And if we filled up our second shell, we moved out and put the remaining electrons on our third electron shell. Again, the maximum number that third shell can fit is 8. So the second and third shell can both fit a maximum of 8 electrons. They might not always need to, like in aluminum, the third shell only needs 3 electrons. And in nitrogen, the second shell only needs 5 electrons. But they have like the capacity, they have the ability to fit 8 electrons on them. It's kind of like the car that you drive. If it's like a normal 4-seater sedan type of car, it has the capacity to fit 5 people in there, but it probably only has 1 person in there, that being you at a time, maybe 2 or 3 people if you're driving around your significant other or you have some kids along with you. So just because they can fit 8 doesn't mean that there will always be 8 electrons on there. It all depends on the type of atom that you are dealing with. All right, any more questions before we do a couple examples together?
Yes, I was off Tuesday or wasn't able to join, so I'm pretty sure you went over this, but it says neutral atoms have equal protons and electrons. How would you be able to determine which a neutral atom and what's not?
So, good question. All of the atoms that we're talking about in this class are going to be neutral atoms, which means the protons and electrons are balanced. There are other types of atoms that are out there. Sometimes atoms get extra electrons added onto them that makes them more negative. Sometimes atoms get some of their electrons taken away from them, which makes them more positive. But the atoms that we're going to be dealing with, especially with doing all this counting, are all going to be neutral atoms, where they have an equal balance of negative electrons and positive protons.
Okay, thank you.
No problem. Great question. All right. So let me really quickly bring up a whiteboard up here. Hold on, where's the thing? There it is. All right. Oh, this one. All right, so this is a Jamboard. If you haven't seen one before, it's like a online whiteboard that I can draw on, and you guys can either look at directly with the link that I put in the chat, or you can just watch it on my screen here as well. That's totally fine. So I'm going to have you guys help me draw out some electron shells. So we'll start off. Let's see, what's a good one? Ooh, we'll do. What's after lithium? I think it's beryllium. So the atom beryllium with the symbol of Be has an atomic number of 4. So how many electrons are in our beryllium atom?
4.
4.
4. Exactly. We talked about on Tuesday how the atomic number, this guy right here, is equal to our protons, but it's also equal to our electrons, which we're focusing on today. So let me draw some shells around beryllium. I'm going to go ahead and draw all 3 shells, even though we may not need all of them. So we have 4 electrons in beryllium. So we start off with our first electron shell. How many electrons can we fit on our first shell?
2.
2.
2. Exactly. So I'll go ahead and fill in 1 electron and 2 electrons on our first shell. So we just used up 2 of our electrons. So it means that we have 2 more left. So how many electrons then are going to go on our second shell right here?
2.
2.
2, exactly. We'll go ahead and put them like on the sides. 1 and 2. So we have now run out of electrons. So we didn't even need the third shell for beryllium. We were able to fit 2 on the first shell, but then that one got filled up. And so we put the remaining 2 on our second shell right here. All right. Very nice. Good work. Let's go ahead and bring up a new board. Let's do a little bit larger atom, something like, we'll do fluorine. So fluorine has an atomic number of 9. So how many electrons do we have in fluorine?
9.
9.
9. Bingo. 3. So we've got 9 electrons in fluorine. So as always, we start on the first shell. So how many electrons can we put down on this first shell?
2.
2.
2. 1, 2. So now this first shell is all full. We can no longer fit any more electrons on the first shell here. So how many electrons do we still have to go for fluorine? How many electrons are left over?
7.
7. Bingo. So how many electrons can we put out on our second shell here?
7.
7. Exactly. See, you guys are getting the hang of this. So we can fit 1, 2, 3, 4, 5, 6, 7 electrons on our second shell. We haven't filled up this shell yet, so we don't need to do anything else. And also, that is the remaining electrons. So we have now put all of the electrons down. So 2 electrons on the first shell and 7 electrons on the second shell gives us 1, 2, 3, 4, 5, 6, 7, 8, 9 total electrons. So we have now put all of fluorine's electrons down on its shells. Again, we didn't even need the third shell because we didn't have enough electrons to make it out there. All right, let's do one more example. Let's go really big this time. Let's jump up to, let me think, what's a good one? Ooh, chlorine. Chlorine is a good one. Chlorine has an atomic symbol of Cl, and chlorine has an atomic number of 17. So, how many electrons are in chlorine?
17.
17. Bingo.
Okay.
Let me put down our shells here.
So the number that's on the periodic table that goes to each, are they considered elements or?
You can
so
say
the number
element,
is
you
how
can
many?
say atom. It's the kind of a different word for the same thing.
Okay. So that number that it has on that little square, that's how many electrons it has and protons.
Yeah. The top number, the one that's smaller, that's called the atomic number, and that is the same as the protons and electrons.
Okay.
The bigger number, the one that's like on the bottom, and that's usually, I forget exactly what it is for chlorine, but it would be something like, I don't know, like 40.1112 or something like that. That's the atomic mass, and we use that for figuring out the neutrons. We do that subtraction with the number. But the atomic number, the one that's up here, that is how many electrons are in a neutral version of that atom. Exactly. All right, 17 electrons are in chlorine. So how many electrons can we put on our first shell here?
2.
2.
2 electrons go on the So we put down those 2 electrons. So how many do we still have to go?
15.
15.
15, bingo. All right. So how many electrons can we fit on our second shell then?
8.
8. 8.
8, exactly. Maximum of 8 electrons on the second shell. No more are allowed. You can have fewer than 8, but you cannot have more than 8. All right. 1, 2, 3, 4, or excuse me. 1, 2, 3, 4, 5, 6, 7, 8 electrons on our second shell that we have put down. So how many electrons do we still have left over?
7.
7.
7. Exactly. So we put down 1, 2 plus 8. We've put down 10 electrons total so far. So we have 7 electrons to go. So how many electrons are going to go on our third shell?
7.
8.
7. Because remember, we only have 7 more electrons left. We could fit
Okay.
We could fit 8 electrons on the third shell if we had to, but for chlorine, we don't have to. We only have 7 more that don't fit on the first or second shell. So we only need to put 7 on the third shell. 1, 2, 3, 4, 5, 6, 7. So let me do a quick check here. We have put down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 electrons, which is how many that are in chlorine. So this is what an electron diagram of chlorine would look like. We've got 2 electrons on the first shell. We've got 8 electrons that fit on the second shell. And we have 7 electrons that are left over that go on our third shell. So that is how electrons get organized around the outside of atoms. We start with the first shell. When that gets full, we move on to the second shell. If that gets full, we move on from there to the third shell. With 2 maximum on the first shell, 8 maximum on the second shell, and 8 maximum on the third shell. All right, very excellent job on those 3 diagrams, guys. Thank you for helping me out with that. Does anybody still have any questions? Anything about the electron shells that you are a little bit confused about still?
No, not for me.
Oh,
No.
No.
awesome. Great. It did sound like you guys are starting to pick it up a little bit more, especially as we went through it together. So that is perfect. All right. So let's jump back to our normally scheduled notes here. There we go. Awesome. So start with the first shell, work your way out from there. Make sure it is based on the number of electrons that your atom has. So the reason why we spent all this time talking about electrons and electron shells is that the electrons that are on the outermost shell of an atom, so like these 5 right here, or these 8 right here, or these 3 right here, are actually really important for a lot of the chemical properties that atoms have. Remember how earlier in the term we were talking about like physical versus chemical properties? A lot of the chemical properties of an atom are based on the electrons that are in its outer shell. One of the reasons for this is that atoms are, well, I always say that they're like the happiest when their shells are full, or that they want their shells to be full. Obviously, these are tiny microscopic particles. They don't actually have wants or feelings, but they're the most stable, they're the most kind of secure when they have full outer shells. So I like to think about it as they really want those outer shells and they're to be full. And they can accomplish this with a whole bunch of different ways that we're actually going to talk about in a lot more detail on either Tuesday or Thursday next week. I can't remember which one. But we'll talk about how atoms work together in order for their shells to be full. So like sometimes they'll share electrons with other atoms. Sometimes they'll give away their electrons and other atoms will take the electrons from them, all in an effort to make that full outer shell, either to have a full set of 2 in the first shell or a set of 8 in the second or third shells. So when they do this, when they move their electrons around and put them in other shells or share them with each other, that happens during those chemical changes, those chemical reactions that we were talking about. And so how reactive an atom is, we mentioned that was one of their chemical properties, was reactivity. How reactive it is based on how quickly it wants to take or give away electrons in order to get that full shell. So elements or atoms that have an almost empty or an almost full outer shell are more reactive. The way I think about it is like they're so close to getting full outer shell. If they can like just give away that one last electron, or if they can just take one more electron from somebody else, then they'll be able to have a full shell. So things like, if we go back one slide, sodium has just one little lone electron that normally sits on his third shell. So if sodium could somehow give away that electron, it could then have a full second shell and it'd be nice and happy. Similarly, chlorine, which we just did that example and said chlorine has 7 electrons on its outer shell. If chlorine could just get one more electron in there, then it would have a nice full round 8 electrons on its third shell. So sodium and chlorine are both very, very reactive atoms. They really want to give away or take that last electron to get that full shell. A lot of times they react together in forms like this in order to make the compound sodium chloride, which you guys all probably know more as table salt. So table salt is a very stable, obviously very steady compound, but it's built from these highly reactive compounds coming together and going through a chemical reaction in order to create a more stable compound. So sodium in the pure sodium state is so reactive that even if you expose it to just a little bit of moisture in the air, it'll like catch on fire and almost explode. All because it has a very, very high reactivity. It really wants to do something with that one lone electron. Other atoms that have super full outer shells, that have their outer shell filled up already, they're less reactive. They don't really want to be reacting with all those other elements on the table. They're happy just doing their own thing. So like neon and argon, we talked about earlier, full second shell. Argon has a full third shell. They are like sitting fat and happy. They don't want to be messing around, giving or taking away anything. they like their electrons right where they are. They don't want to react with other atoms and move their electrons around. The reactivity of an atom, how kind of it'll chemically react with other elements, that is all determined by the outer shell electrons. So like these guys over here, we were just talking about sodium, but things like lithium and potassium, very, very violently reactive metals.
Is
Will almost
lithium like, is
explode.
that like the medication?
It's similar to the medication. The medication that you get is like a modified form that's a lot more stable. This one is like if you got 100% pure dose of lithium or like potassium, that would be explosive. That would be very violently reactive with stuff. Most of like the potassium in our body is already reacted with other stuff, other chemicals that's in there. That makes it more stable. This is like if you have a totally pure, 100% purified version of this compound. It's super, super unstable and explosive. These guys over here, though, are the opposite. So like neon and argon, we were already talking about, but also things like helium and krypton. These are much more stable. They barely react with other atoms. They already have all the electrons they could want and need. So they're happy to stay on their own and not do any sort of mixing with the other atoms that are out there. So again, this reactivity, this chemical property that atoms have, some of them are more reactive, some of them are less reactive, like these guys, but it all depends on those outer level electrons. And next week, we'll talk about exactly the main ways that atoms with those different electron numbers can come together in order to try and make a full set of 8. All right, so the final thing that we're going to talk about today has to do with sort of the major categories that we can place atoms on the periodic table. So you may have noticed that this kind of condensed version of the table that I've been showing you guys the last couple days has these different colors on it. That's not just for fun or to make it look cool. Those colors represent the different groups that we can put our different atoms into. So the biggest group is the metals. Those are the yellow ones right here. So things like we have aluminum over here, zinc, nickel, silver, gold, iron, magnesium, calcium. These are all metals. We have the nonmetals, which are things like helium, oxygen, carbon, hydrogen, which is all on its own over here. All the other nonmetals are kind of grouped up around here. And then in between them, literally on the table, and also in terms of their traits, are the metalloids. So they're sort of like metals, sort of like nonmetals, and so they literally fall in between nonmetals and metals and this little purple zigzag line on our periodic table here. So the metals have one set of properties that we're going to talk about. Nonmetals have basically the opposite set of properties. And then metalloids kind of fall somewhere right in the middle. So when you think about the properties of metals, I want you to picture like the aluminum foil that is in your house, in your kitchen. So metals in general, not every single metal 100% is like this, but for the most part, metals are shiny, right? So they're very reflective. They produce lots of light that bounces off of them, just like the aluminum foil. They tend to be solid at room temperature. So things like aluminum, iron, gold, silver, it's all solid. It's all solid pieces of material when it's at like 70, 80 degrees Fahrenheit. Metals also have some cool properties in terms of how they are shaped. metals are what's called malleable, which is a fancy science way of saying that you can squish it, you can bend it, you can hammer it down flat, just like the aluminum foil in your house comes in those flat sheets that you tear off. Most metals can be worked with. We can bend and shape them and squish them down and flatten them into like a sheet or a plate of some kind. Related to that, metals are also ductile, which is just a fancy science way of saying that we can twist them up and pull them into a wire. So pretty much all the wiring in your house is made out of metal, especially things like copper and aluminum. So like these little strands, these little twists of metal right here are what provide the electricity that runs throughout your house. And one of the reasons that they're made out of metal is because metal, we can work with it, we can twist it up, and it's not gonna like break or shatter or fall apart, right? It's pretty hardy, it's pretty bendable, it's pretty good to work with. The other reason why we use metal in our house for electricity, and why you also use it to cook things on the stove, is because metal is an extremely conductive material, meaning that electricity and heat flow across metal really, really easily and quickly. That's why if you put your pot on the stove and crank up the heat, even though all of the heat is coming to the bottom of the pot, after a minute or so, if you touch the top of it, you're gonna burn your finger, right? That's because the metal that the pot is made out of is very, very conductive of heat. It's able to move the heat that it's getting from the burner all around the pot. That's why metal makes such good cooking material. It's because we want that heat to come through the surface of that metal and touch the food and cook the food. That's why you don't see a lot of times people cooking in plastic or wood, right? They just don't move the heat as well as metal.
So metal is an element?
Metal is not an element itself. Metal is a big group of elements. So all elements right here are metals, which means for the most part, they share most of the properties that I'm talking about. So things like aluminum, cobalt, nickel, iron, gold, silver, these all have these same general properties that I'm going over here. They tend to be shiny, they tend to be workable, we can squish them, we can squeeze them, we can pull them into wires, and they tend to be good at conducting heat and electricity. So electricity lines are made out of metals like copper and iron and aluminum because they're able to carry that electricity all through those wires and into the different devices in your home. So conductive just means that heat and electricity flow very easily through it. So those are our metals. Again, picture like aluminum foil. Aluminum is an element, and aluminum foil is made out of aluminum. And it has all of these characteristics. So most metals have these physical properties right here. On the other hand, the other side of our periodic table, nonmetals, has basically all of the exact opposite properties of metals. So nonmetals tend not to be shiny, unlike metal. For the most part, they are gas at room temperature. So stuff like oxygen and nitrogen and neon, those are all nonmetals and they all are gases at room temperature. You have to get them very, very, very cold to get them to be liquid or solid. Nonmetals are very bad conductors. This is why if you're cooking with something on the stove, a lot of times you use a wooden spoon or a wooden spatula to like move stuff around or cook in the bowl, right? Because wood is mostly made out of carbon, which is an important nonmetal, and carbon does not transfer heat well. If you leave that wooden spoon sitting in your boiling pasta water for a minute or so, you can probably come back and pick up the handle of the spoon, no problem. If you did that with a metal spoon or a metal spatula, you're going to burn your hand if you try and touch it after it's been sitting in the boiling water. The metal spoon conducts the heat all the way up to the handle very quickly. The wooden spoon does not. It is a bad conductor. Same thing with plastic. Plastic is also mostly made out of carbon. And that's the reason why, not that I would suggest this, don't do this, but if you did shove a plastic fork into an electric socket, nothing's really going to happen. The plastic and the fork cannot move that electricity around and into your body. On the reverse side, if you do that with a metal fork, you're going to have a real bad time. The metal in that fork is going to move the electricity out of one end of the socket through your body and into the other end. And you're going to get shocked and feel really hurt about it later on. So nonmetals are bad conductors. They don't move heat, they don't move electricity well at all. Nonmetals, when they are solid, so some things like sulfur are a solid at room temperature, but they are very brittle, meaning that they break and they shatter and they crumble apart easily. Unlike our metals, which we can squish down and twist up and bend around, nonmetals tend to just break and crumble and shatter into a million pieces if you try and do anything with them. So again, basically exact opposite properties of metals. Tend to be gases, can't really be used for electricity. You can't bend or squish them. They're just gonna shatter apart in your hands. So not only are they opposite from the properties, they're also literally on the opposite end of the periodic table, except for poor little hydrogen. He's hanging over here all by him lonesome. Finally, our metalloids, which are literally in the middle in between these guys, also have some kind of in-between properties as well. Metalloids are solid at room temperature, just like metals. So they tend to be solids. They don't tend to be gases or liquids when it's room temperature. However, like nonmetals, they tend to be hard and brittle. They tend to be very breakable, very crumbly, not very workable like metals are. They're not malleable and ductile. They can't be squished and bended around. They are more likely to snap and crumble. Metalloids can be good conductors, sometimes. They're very good at being semiconductors, which, just like the name suggests, means that they are sometimes good conductors. Those sometimes being under certain conditions. Usually they have to be in a very pure state, and they have to be protected from things like dust or other elements around them. Otherwise, they're not good conductors. So computer chips, for example, use lots of semiconductors. Lots of metalloids like silicon go into computer chips. Because inside your computer, the conditions are able to be monitored really closely and set up just right in order to have them be extremely good conductors. If there are a lot of semiconductor plants around Austin because of all the tech stuff that's going on around here, and if you've ever seen people make semiconductors, they have to be in those like white dust jumpsuits to make sure that no like dust or particles gets into the semiconductors. Because if there is some sort of outside contamination that comes into contact with the metalloid, it's not going to be a good conductor anymore. So that's why they get the name semiconductors. They can be really, really good, efficient conductors, but it's not like all the time like metals are. They have to be put in very certain circumstances, very particular conditions in order for that to work. Silicon is a big metalloid. It's found everywhere. It makes up a lot of sand on the beach and glass. So like glass panes that go into windows and houses and stuff is made out of silicon. And that is a type of metalloid. Like I mentioned earlier, it's also very important for computer chips. So the reason why the area of California, where like Google and Facebook and Apple are all headquartered. It's called Silicon Valley, not because there's a whole bunch of like silicon in the hills there or something like that, but because silicon is so important in the computer chips that these companies are based off of. So those are our metalloids. Again, some properties that are kind of similar to metals and some properties that are kind of similar to nonmetals, which is why they go right in between in our periodic table. Some more stuff about reactivity that we're not really going to worry about. Again, we have a super low reactivity group of our nonmetals over here. These are the guys that have that full electron shell on the first and second and third shells. And in fact, they are so low reactivity that scientists even came up with kind of a funny, silly little name for them. They called them the noble gases. So group 18 means they're in the 18th column of the periodic table, the very last column of our table here. And they call them the noble gases because these guys are so non-reactive. They're so unwilling to mix with all the other elements on the periodic table that scientists thought they're kind of like rich nobles from medieval times that didn't want to mix with all of the lowly peasants that make up the rest of the population. So they're so rich in electrons, they're so full of their electron shells that they cannot even be bothered to mix with all of these lowly other elements down here. So they tend to just cluster up in groups of their own. They don't want to mix with anything else. And again, it's all because they have those full shells of electrons. There's also carbon right here, probably one of the most important elements on this group, not just an important nonmetal, but for us, it's the most important element on this group because carbon is the basis of all life that has been discovered so far on Earth. So everything, all of our energy comes from breaking down carbon. All of these cells in your body have membranes that are built out of carbon, and the structures in them are mostly built with a carbon skeleton. So us, our family members, our dogs and cats, the trees and grasses that grow outside, the bacteria that live in the soil, the ants that build their mounds, they're all made based on carbon. We call them carbon-based life forms because that's everything that we've discovered. So carbon is an extremely, extremely important nonmetal and extremely important element in general. It's what's responsible for all of the energy in your body comes from breaking down the carbon that is in the food that we eat, the other plants and animal organisms that we eat for energy. So those are our major groups of elements on our periodic table. We have a whole bunch of those shiny conductive metals. We have a little group of brittle, non-conductive nonmetals. And then we have this little in-between group of brittle, semi-conductive metalloids running right down the middle here. All right, anybody have any questions about our different groups of atoms, our metals, metalloids, and nonmetals?
No.
No.
All right, cool. So for the daily assignments that got posted for today, and then the one that'll be posted next week on Monday, today's has to do with those electron shells that we were talking about earlier. And then Monday's has to do with the metalloids, nonmetals that we were just going over. So today's assignment has to do with the element oxygen. oxygen has an atomic number of 8 and an atomic mass of basically 16. So the first part of the daily assignment for today is exactly the same as what you guys did for the last couple days. I just want you to tell me how many protons, how many neutrons, and how many electrons are in oxygen. So for the most part, people did really, really well on that with the assignments that went up on Tuesday and yesterday. So that should hopefully be pretty straightforward. If you need a refresher on how to figure out those numbers, you can always go back to our Tuesday notes on atomic structure or rewatch the video from Tuesday's class. This electrons number is going to be important to figure out though, because the next 3 questions, I want you to tell me what are the electron shells of oxygen going to look like. So I want you to tell me how many electrons are going to go on the first shell of oxygen, how many, if any at all, go on the second shell, and then finally, how many, if any at all, go on the third shell. Again, you might not need to go to the second shell or the third shell, so you can either write 0 or none if there aren't going to be any on there. But if there are going to be, I just want you to tell me how many electrons. So first shell, second shell, third shell of oxygen, how many electrons are there going to be? So pretty straightforward. Again, those first several questions are stuff that we've been doing for the last couple days anyway. And then if we jump ahead and look at the Monday assignment that'll go up for your asynchronous daily assignment next week, we have a little chart comparing the metals, metalloids, and non-metal. So we have our 3 different types of atom across the top here. And for each one, I want you to tell me, does the description here match with 1, 2, or 3 of these substances? So maybe the description only matches with 1, or maybe it matches up with 2 of them, or maybe it matches with 3. There could be more than 1 that match the description. So don't just be like, oh, that's got to be a metal. Oh, that's got to be a non-metal, and move on. Because it also might describe a metalloid or a different metal or non-metal as well. So for each one of these descriptions, things like being a gas, being brittle, being a semiconductor, being malleable, I want you to tell me, does that describe a metal? Does it describe a non-metal? And /or does it describe a metalloid? So again, that'll be going up for your Monday assignment that you can do for attendance. And if you need help with it, you can always reach out to me, but you can also jump back to the notes from today, which are our Thursday notes about electron shells and reactivity. All right, does anybody have any final questions about the electron shells, the metal, metalloids, non-metals, or any of the homeworks that I've shown you guys here so far?
No.
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 All right, awesome.